Welcome all to the ninth session, which is a practical session. So feel free to ask questions and I'll try to answer them.
Sorry, I had a question about the reparameterization of the negative binomial model. I just wondered, is there any motivation or what's the intuition for the reparameterization, I guess?
You mean the one via just simply taking, so what is the question exactly? Is it the tau reader or is it the, so I guess I'm just trying to gauge whether you want to inquire about both variables that we change in or just one of them.
Yeah, I think both variables still confuse me a bit.
Okay. So I mean, I guess the negative binomial. So remember that if this tau is known, then it is a negative. It is a GLM. So in that case, you wish to have it parameterized in the same way that you would have the rest of the GLMs, right? So you need to identify the mean. And so that's why we take the mean basically in the reparameterization. So just in the same way that when we were defining exponential dispersion families, we changed from one parameter to another to write it in terms of a mean, because after all, I mean, GLMs, what we're really interested in is modeling the mean, right? Remember from the very beginning, from the first session. So then we wish to have the mean in the new parameterization. And then when it comes to tau, we could have left it, as the inverse of tau, which is the R. But I guess it's a bit more intuitive to write it as we're writing it, because remember the negative binomial, we introduce it to model over dispersion. And if, in Poisson, in the Poisson model, and so if the variance in the Poisson model is the mu, is the mean, then whatever we add to that, it makes a bit more sense that basically, the parameter that we have is proportional to the new bit of variance, right? Rather than being sort of inversely proportional.
Okay. Right. And then, sorry, thank you. And then, sorry, I did have a follow-on. With since tau goes from being when R is is an integer, and then we just let tau be bigger than 0. For the factorials in the density function, do they just become gamma functions?
Correct. Yeah.
Okay. Thank you.
So this is in the theory notes, because that's the way to generalize it. Yes. So the factorials, they are special cases of a capital gamma function, and so in the notes, I think I wrote the PDF, so that well, not PDF, MGF, probability mass function, and so that's basically how you argue it. Yes.
Right. Yeah. Thank you.
No problem. Right. Any questions about practical 4?
If I don't know whether it makes sense to kind of ask questions going through it. The main question which came to mind straight off on the subject of negative binomial models is, how are we fitting that parameter theta or tau or R?
Maximum likelihood estimation. So negative binomial is a perfectly well defined. It has a perfectly well defined density with respect to the counting measure. But anyway, a density, and you can therefore define the likelihood. And once you define the likelihood, you can maximize it.
And didn't we say something about having to treat that parameter as fixed when we were doing some sort of analysis in lectures? Or am I That could be an erroneous memory.
Yeah, let me just think if I said something like that. Don't think so.
I can't see it written down here actually.
Because that's that's precisely, the point of introducing the negative binomial is that we can play around with that parameter to absorb, any dispersion that we had. So.
You made a comment in lectures that on the example sheet which showed that the family is an EDF if we have R known.
Right. Yes. Right.
So how exactly does that correspond to fitting R?
Yeah. So but that doesn't happen in practice.
Okay, so we just don't treat it as an EDF. We do some different sort of maximum likelihood.
Yeah, we use maximum likelihood. Maximum likelihood has nothing to do with EDFs or anything like that, right? So once you have a density with respect to a dominating measure that works for all of the parameters of the family of distributions that you have, which again doesn't have to be an EDF, then you can find the likelihood and you can maximize it. So.
Is that where the expectation maximization algorithm comes in, as opposed to using some sort of Fisher scoring or
So the expectation maximization, I introduced it for the zero inflated models. And this is so expectation maximization, what it requires is that you have, a set of observable random variables, which of course you should always do because that's the data. And there is also a set of unobserved, or also called latent variables. So if you can phrase your model as as one having those two sets, then you can do expectation maximization. And it turns out that actually negative binomial can be phrased as that. So you will have seen this in the example sheet, but I haven't covered that in lectures yet. So I will talk about that on Friday. So you could apply expectation maximization, but I didn't introduce it talking about the negative binomial at all. In fact, negative binomial, is simple enough to do maximum likelihood estimation, which is much quicker than expectation maximization.
Have you got a bit more intuition as to what expectation maximization is? And maybe I just haven't thought about it hard enough, but it seems a little bit of a strange idea, kind of switching from one to the other.
Well, okay, so I guess I don't have a very good answer that will, somehow magically make it work in your head, but you can certainly show, and it's not a difficult proof, you can definitely show that the log likelihood for the usual model in which you don't have the latent variables, that in that one, that it grows for every, that is non-decreasing for every iteration.
Yeah.
Again, I guess yeah, so I think if you want to get any intuition, then you have to look at that proof, basically. Yeah,
it's not on the example sheet anywhere,
it's not on the example sheet, but it's a very standard one, so I'm sure it's on Wikipedia.
Thanks.
If you don't find it, then drop me an email. But it is, I think it's there. If you don't find it, then let me know. It's like a two-liner.
Okay, great.
Yeah.
There seem to be a couple of questions in the chat.
Sorry. Yeah. Let's see. Let's see. With the first Poisson model, why do we choose to include the interaction between BDP and sex? Well, I guess, so let me copy this and then it'll be. And then we can do some, so we can examine the data through a few of these things. Okay, and did I include, let's see, tau, okay, so I'm just thinking whether indeed that was just playing around with things or there was a better reason. Yeah. So there is no, at least not one that, so I cannot give you a very satisfying answer to that. Bertil, let me just see. Yes, okay, yes. So I forgot one, yes. Right, so yeah, so that's what I was guessing, that there should be something I looked at some years ago, which is that if you look at, so, you know, this by function, is, so what it tells you to do is to say, well, do the function in the last argument, right? Which is, you know, sort of divide the data in tables, and do so for the count. So the data is the count, and we're going to divide the tables according to the treatment and the sex variables. And so then you have this here, and you know, you realize that, of course, there is quite a difference. I mean, when it comes to, let me just remind myself which one's which. So masculine, well, man, yeah, okay, so that's wrong, actually. That's not sex, that's gender. Anyway, so man, so if we have treatment or not, then it seems to make a difference. And then clearly for a woman, right, we have here that this is quite different from the man in general. And also, if we make it particular to treatment, then you know, if we specify the treatment, then clearly there is a difference as well. And there is also a difference between, you know, this one and that one. So clearly there are some interaction effects, or there are potentially some interaction effects, right? So that's the answer. Yeah. Yeah. Okay. Then Benjamin, in the first part of a practical, we compute phi hat 1 and phi hat 2 to see if the models are good fits of the data. Okay. Yeah. When running the pi chi-squared, the pi chi-squared, what is this? Tests, can we not use the deviance from the models mod 1 and mod 2 directly, or would something be wrong in doing that? You can, but and I think, do I have it here, or is it in the next bit? Then maybe it's in the next bit. You can do, but I did say when we introduced, the theorems, I said that the approximation. So I said that the phi hat, the generalized Pearson statistic, and the deviance, as you get more and more data, or in the small dispersion asymptotics, they will be sort of converging to the same quantity, and so they are actually equal up to some negligible terms. But the phi hat actually is in some sense closer to the limiting distribution under these SDA asymptotics, and so it is always preferred over the deviance if you can compute it, basically. So I guess both for an exam and for a practical sort of situation, I would use the phi hat if I had the choice of both. Of course, in an exam, you may not, or actually in the practical life, you may not, because you've been given some analysis, which is, for instance, the summary in the function, right? Which doesn't include the phi hat. Okay. Okay, so Benjamin, yeah, and then Patrick. How would we run a likelihood ratio test between zero inflated models with intercept, maybe more parameters modeling the PI, and a model without zero inflation? Okay. So I'm going to assume you mean, yeah, so just for simplicity, let's take a zero inflated model. Well, let's take a zero inflated Poisson model with just an intercept in the probabilities versus a Poisson model, full stop, without any of these. So, I mean, how you create the likelihood ratio test statistic, I think, should be clear, shouldn't it? Because, I mean, after all, you're just taking the likelihoods and maximizing them, and then taking the difference and maybe multiplying by 2. So, I mean, in that sense, I hope there is no issue. I guess your question is regarding the limiting distribution. So, in such case, what you get, let's see. That's a good question. Let's see. I mean, okay. So I guess I have 2 things that I can comment on here. Firstly, it applies to both. You could view this as, the parameter could be the P variable, right? And remember that, this P variable, so generally speaking, I think I assumed it to be between 0 and 1, not including the boundaries. So it would correspond really to, Poisson would correspond to a model that is in the boundary of the parameter space. And again, we would have the same situation as, for instance, in the negative binomial model versus the Poisson, or the other way around. And I would imagine that you get this mixture of a Dirac delta at 0 and the chi-squared at 1. In fact, I think you do. But an alternative in these cases, in which it's not very clear what you would get as a limiting distribution, is to do bootstrap, to do for instance, in this case, I mean, we are looking at parametric models, so then you should be using parametric bootstrap, because using parametric bootstrap will give you more power in the test than if you use non-parametric bootstrap. For those who don't know what parametric bootstrap is, I will talk about it on Friday. So you're sort of jumping ahead a bit, but yeah, that's what you could do there. So it's not really. I don't think the problem would be in setting up the statistic, because the statistics is again 2 times the difference of the likelihood of the maximized likelihood. So it's a bit more about what is the limiting distribution, if anything, or what sort of distribution there is, that you can compare it to, right?
Yeah, I was thinking it might be this, like this half delta plus half chi-squared one. And I was thinking, but the thing I was kind of wondering about is if we add in other parameters, would it be a half delta plus a chi-squared, say 2 or 3? Or would it change the nature of the delta thing as well?
Yeah,
or
exactly.
Would it just be the chi-squared thing that changes?
Yeah, exactly. So I don't dare to give you an answer, because these things are not computed. There is no table for these things. So I basically don't dare to give you a precise answer as to what would be the limiting distribution. So this is why, I mean, with these things, and also for other reasons, because I mean, after all, we're talking about limiting distributions. You'd rather have finite sample distributions than the parametric bootstrap is more, it just works better, and you don't need to identify any limiting distributions, because it's the finite sample distribution that matters. So this is why I will introduce the parametric bootstrap in the next session. Okay, what else do we have here? Why do we make sex and center factors but not treatment? Did we not? I guess not, if you say that. Okay, so we had, I guess we did have 2 only treatments.
Yeah, sorry, it wasn't sex, but BP that was factor, but still the question was the same.
Sorry, can you say that again,
Why
please?
didn't we make treatment? Yeah, sorry, I made a mistake when I asked the question. It was, why do we make BP the end center, not sex and center? The question is still, why didn't we make treatment a factor?
Right. Yeah, I think it's probably because I'm not doing any analysis in which I'm wishing to
Isn't it the case that it doesn't matter as long as you only have 2 factors?
Yeah, it doesn't. That's why I'm just thinking, whether there is a more, there is a reason that depends on the functions that I applied afterwards.
Okay.
I can't see anything that piques my attention here. Yeah, I mean, I don't think so. Firstly, it doesn't make any difference, at least in a numerical sense. And then this is again, so what I'm looking for is some place where I may have used those variables. Well, where I may have used a function that requires those 2 variables to be factors, but I don't think I have. So it could have just been forgetting about doing it, or just, I don't think it's very important.
Could you just be like explain a bit more what is the use of a factor? What is it? Is it interesting to have some variables that are factors?
Well, I think generally speaking, you do that as your fellow classmate said. So when you have more than two values, then that's important, because so this is what we had in the. I think we talked about this in the previous practical, or in the one before, which is that if you have a numerical variable, then with more than two values, so say 3, then what this means is that once you fit the coefficient that corresponds to that variable, then when you change between different values of the variable, you're assuming that the change in the mean responses is going to be equally apart as you change from one to the other, right? So say that we're talking about a linear model, right? That's the simplest. Then the mean is just, it's a linear function of, it's a linear combination of the coefficients, and each of the coefficient of the coefficients is really the value of the variable, right? And so if you have a variable that takes values 0, 1, and 2, then what's going to happen is that, of course, you're going to, when you take the value 0, you're not going to add anything from that variable to the mean. But then when you have a value 1, you will add, the value of the coefficient. And when you have the value 2, then you add twice as much, right? So you're saying that the influence of each of, the influence of changing from one value to another of the underlying variable is equally sort of apart, in each of them. While if you have factors, then what you're doing is you're fitting, you are you're in some sense fitting different coefficients for each of them.
Yeah. So we change the dimensions when we use factors.
Yes.
Okay.
Yeah.
Thanks.
So if your factor only takes values 0 or 1, it doesn't make a difference whether you sort of tell R it's a factor or not.
It's just whether it is active or not, basically.
Maybe there's something like code-wise which.
Yeah, exactly. So that
the functions won't work. Maybe.
Exactly. So if you want to use like the strict definition of ANOVA or ANCOVA, for instance, sort of looks at factors. Yeah. So this is why I was looking at the functions that I was using afterwards, because it may be that some functions implicitly sort of look for the factors in the model to then do a certain analysis. That can be the case, yes. So that's a bit more of a practical R type of thing to worry about. Yeah. Not quite from a mathematical point of view. So I realized this later on. So I added the very last bit. So this is James. I apologize. Because in the zero inflated models, I added the possibility of having these two zero inflated negative binomials. And indeed, because I added it at the end, then I computed it later, and indeed, it turns out that one of the matrices there that needs to be inverted is singular when you have when you add all of the variables to model the probabilities as well. So you can safely ignore that. I wouldn't be as mean as putting anything like that in the exam.
What does it mean in the context of modeling that when you get something like this?
Well, there's probably so I guess you could have at least two things. So you should always go back to the linear model, right? So when you have an issue with inverting these matrices, which is pretty much what's happening here in the, when you're maximizing the likelihood, then it can be that, you have too many variables, so you have a lack of identifiability, or you have two variables that are, just very, very correlated one with the other. So that must be what is happening here in one of the two.
Yes. Have you got any idea as to which variables could be causing the problem, or if there are just too many parameters? Or
I think it may be that it's too many parameters, because we've got to, and this is something that happens. I mean, I'm not sure off the top of my head I can tell you exactly everything that is going on, but there is generally an issue if the P, so if the probability is a function of the, of the means, in some sense. So if you have that, then there can be an issue. Yes, and I didn't realize that. There can be issues of these kinds, that there is some potential lack of identifiability.
So what do you mean by the probabilities are a function of the means? Is that like a zero inflated probabilities?
Oh yes, of course. Yes, it is. I mean, we're talking about zero inflated here. So in zero inflated, yes. So if you have that, the probabilities have the same covariates that the means would depend on, or more, basically.
Okay, which is what we've got. So you think maybe if we just got rid of one of the variables after the kind of pipe symbol?
It's not necessarily the case, but
okay.
But I guess the other way around is certainly generally a sign of potential issues. So it could be that just one of them is actually the annoying one. So I mean, these things are a bit. I mean, these models are a bit involved in terms of the likelihood. So it's not, it's not that I can give you an immediate answer as to what is causing what, because you need to look at the log likelihood and maybe work out what happens, but it's not necessarily the case that you can work it out easily. So by the way, before I answer Michael's, regarding this one, I guess what it's interesting is that, well, not interesting, but at first picks the attention is that you do get estimates for the parameters. You just don't have the variances, right? And that's because for the estimates of the parameters, you don't need to look at you don't need to look at second order properties of the likelihood, or you don't need to invert first order quantities of the likelihood, because you can just do gradient descent, or the methods of optimization that only depends on the first derivative. While for the variances, you need to either invert first derivatives or invert or actually have second derivatives. And these things, they can be more problematic than the likelihood itself. So Michael, why did we choose to model the BPD sex interaction only? How would we decide interactions to use in general? Yeah, that's a good question, I guess. So it's a matter of doing what we did here in this sort of examination of the data. If you believe that by doing tables that there are interactions, then you're more than free to add them. In general, I would say try to add as few variables as possible, just very simply because you want to have as parsimonious models as you can. you could also decide doing tests. So you could set up, a couple of models and try to decide between them using a hypothesis test. And what two models to choose would be a question of precisely doing this examining of the data. Now, however, note that if you're doing that, it's probably not best practice to just look at the tables and then set a test based on the tables. Yeah. Because what can be happening is that, it can be good practice, but let me say why it could be bad practice. What can be happening is that the data, the data of course is random. So you could get just pretty much anything out of the data. And so if you just look at the data you got, then and set up a test based on that, then of course the test is inherently going to be favoring, whatever you can see in the data, right? So if you, I guess it makes sense what I'm saying, right? So this is why tests, any inference procedures should be fixed before you collect the data. Okay. Now, all of that is true if you can only collect data once. Yeah. Of course, ideally, the ideal world, the scientific method goes in a different way. So you have what Qin Yuan, one of the lecturers in Stats Lab, calls the statistical cycle. I think he calls it like that, which is that, it's very much in the spirit of the scientific method, which is, you observe something in nature, which is essentially, collecting data, even if it's not very quantitatively. And then you create a hypothesis in your head, right? In this case, what we're talking about is, that some interactions should be in your model. And then you collect the data to check that hypothesis. Okay, so then there is no problem there, because the hypothesis, if it just depended on the initial data, then the second set of data will probably tell us that it was a wrong hypothesis. And if it doesn't depend on that, then probably the second set of data will confirm that that it's something inherent in the data. Now, if you can only collect once, generally speaking, you decide these things given your insight of the problem. So it's funny, because I would think that generally statisticians, especially mathematical statisticians, are never going to be confronted with statistical problems, because the statistical problems are really faced by practitioners. And if you have a doctor that really wishes to test all of this, then they will know what type of questions they want to answer. Yeah. So, for instance, if you are really trying to answer the question of, is the treatment, or is the, what was it we were adding? Bipolar disorder, I think it is. Yes. So you could be wondering perfectly, is there an interaction between borderline personality disorder and sex? And so in that case, I would fit, the simplest model that you can that includes that. And so this is what is being done here, basically. I guess that's yet another way of arguing how you choose these things. It's more that you have a scientific question that comes before collecting the data. In this case, whether there is an interaction, and then try to answer that by adding it to the model. And yet another way of choosing interactions is just simply thinking, well, clearly we know from other studies, and this is a bit more like in the sense of this statistical cycle, we know from other studies that actually, the borderline personality disorder and the sex have some interaction, and therefore I should include it, because there are good reasons to believe that that is the case. Yeah. So there is no easy answer to that. I think, in my opinion, it really depends on the modeling, and it really depends on the number of times that you can collect data.
Thank you. But for the kind of, say, you can't do inference after you've done model selection on your data, could we alleviate that by doing a kind of train test split? So we train and test on one half, and then we say also verify on the second half that's unseen.
Yeah, you could do. Yeah, you could do now. So I didn't mention when I said that was an option, and that's actually the simplest of all. It does have an issue, and is that, of course, you've lost half of the data for both things. So of course you get less accurate estimates and less powerful tests and so on. But that's life. Yeah.
Yes, because it seems, say, almost a shame that once you've done model selection on your data, then you just can't use it anymore for inference.
Yes, but it's but it's a very intuitive issue, right? Because it's what I was saying before. So it could well be that your data, because it's completely random, then it's telling you something that is actually not inherent in the distribution that is giving rise to that data, but rather just inherent in the set of data that you took, right? And so this is why you shouldn't be trusting that set of data for then again making conclusions about the whole distribution, right?
Thank you.
Is there like a mathematically valid way of doing like exploratory data analysis? Because of course, if you just sort of like, look at the summary and go, oh, that parameter's got a star next to it, I'll do a test on it. That's.
I wouldn't say that's exploratory, by the way. I would say that's after exploratory analysis. So exploratory analysis, I would call, so exploratory. Okay, so it is exploratory, fine. But that bit of exploratory analysis actually does have mathematics behind it. I guess what I thought you were referring to is this, is these other tables that I was plotting here and this kind of thing. So those, of course, you're not.
Well, I mean, similarly, if you sort of look at those tables and then sort of choose what kind of test you're going to do, that's a similar kind of issue, isn't it?
It is. No, it's 100%. I guess what I want to say is that if you have a star, in a row of your summary, then that star has a meaning that is mathematically justified in some sense. But yes, but they both are, extremely dependent on the set of data that you got. And this is why, doing stats in practice is actually a very, it's a very subtle exercise and complicated one. So I think if I would like you to take one sort of take-home message from this course, is that actually you should be extremely careful and cautious about what you're doing. And that is not generally the case in sort of very, sort of machine learning communities or in even in companies at all. So one of the companies I advise, essentially they really, the interest in having me there was that they really, really want to convince people who are not the data scientists that one should be a lot more cautious with these things. So it's more about finding examples in which you're totally doing something wrong that can be understood by a completely layman in layman terms. And this is very important, I think, in the models that we'll see in classification, because they become very, very complicated. So not only do you have to sort of take into account all of these complexities that we're seeing in very simple models, but also you need to understand that actually you have an even more complicated model. So it really, it even requires more, for you to be more cautious and careful.
Is there any sort of like way you can turn cautious and careful into like, you know, maths?
I guess the reason why we know that we have to be cautious is because we understand the assumptions under which we prove the theorems together with the
Well, yeah, I mean, like, because if you see it, you know, if you see a star next to some row of your, you know, one of your parameters, of course, that means that if you test that parameter, but individually you get that significance. But of course, we know, like, from multiple testing that, you know, if you're looking at all of the rows and seeing if there's a star next to any of them, then you have, you know, you have to change the significance you're talking about.
Yeah. So I mean, what maths gives you is, you know, you have a set of assumptions and you have a set of conclusions, and generally speaking, the assumptions are not satisfied, and so that tells you that you should be careful. And the conclusions are not even those that you're using, because, for instance, you have limiting, you know, you have asymptotic results, and that's not really what you have in practice. So this is why, you know, doing any of this is subject to cautiousness, right, or to being careful. And, you know, get one way to go beyond that, or maybe, you know, in terms of the two. Firstly, is to study robustness, which I think there is a part 3 course now on that. And robustness is very important for this very reason, because, of course, you should be wondering, okay, so what if I'm using these models when the models are not right? So that's a way to address, you know, whether you should be cautious or not. And then there is also finite sample results rather than asymptotic results. And this, some of you may have seen in, I forget now the new course in part 2, but there is one in Lent that was given by Rajan Shah, and that it introduces what are called, you know, concentration of measure techniques. And this concentration of measure, precisely what it tries to address is, you know, these probabilities of, so say, you know, probability of a you know, parameter being in a confidence interval. Well, the way we analyze that is with asymptotics, but it can be that you can understand the measure that you're assigning to that set, and that's basically concentration of measure results. So these are you know, these are hot topics. I mean, these are things that are being used in research, these two things at the moment, for these very reasons.
Sorry, did you say that concentration of measure was something done in causal inference? So I didn't go to the course.
No.
Or did you say it was just something that?
Maths and machine learning, I think.
Yeah, maths of machine learning, that's the one, yes. Part 2 in Lent. No, so all I'm saying is, if you, so generally speaking, when you have inferential procedures and you want to analyze them, so say, for instance, a confidence interval, then what you're looking at is the probability of something happening. In the case of a confidence interval, is a parameter being in a confidence set. And so that probability, generally, you know, traditionally, you would study it asymptotically as you get more and more data, because then things sort of simplify. But nowadays, we're not really doing that only. We're also looking at, you know, that probability and trying to understand it without having any asymptotics. And that's where concentration of measure results come in handy, basically.
Okay, yeah. Thanks. Yeah.
No problem.
Can I ask a really basic question just on the implementation of R?
Yeah.
When we do our initial box plots on the self-harm data, the non-log box plot gives me like a funky thing with colors and a box plot, and the other thing just gives me like a top line and a bottom line. What's going on there?
Yeah, that's generally because of the, so I think, so the log here was applied because clearly there is, you know, there are some thin tails, and a lot of mass around the zero, right? And if you take the log, what you will do is just to compress it a bit more, and then things will be in some sense in the same scale. And this is a bit what this is telling you already. So this is telling you they're not on the same scale. Look at, so I forget what the bars are. So that little bar that is above the red and above the green, I believe that's the third quartile, I think. And so clearly this is, if you forget about the colors for a second, what this is telling you is that 75% of the mass of the data is already at that bottom level, right? I don't know what I said, 3/4, I don't know what I said, of the data are already there. And another way of telling you, this shape of the data, of the empirical distribution of the data, is by saying, well, there is the crazy accumulation of values, in those very, very small values. So that's basically what this is telling you. While then when you take the log, things sort of become, they live in the same, in a much more similar scale. And so it doesn't need to tell you anything about that accumulation. That's essentially the idea. Although I appreciate that, of course, the zeros are the zeros, but yeah.
So what exactly is in that plot? Is the top line and the bottom line still like the quartiles?
In this one, yeah.
Oh no, the other one, the log plot.
Let me just plot it. Maybe this one, yes. I would imagine not. I would imagine this is just all of the data here.
Just minimum and maximum.
Yeah, I would imagine that. Yes.
But I just don't. The code looks exactly the same in both.
Yeah.
Okay.
Yeah, I see your worry. Yes. The only explanation I could give you is that because they're now on a very similar scale, right? Because they're now units and up to 4 or something, then it doesn't bother to try to explain, that shape, because the shape is important when you have, these different scales, right? So things that are 0, 1, and then things that are 40 times more. So you need to see, you need to appreciate the differences between such different values, right? Or the concentration for such different values. That's my only answer. And I know it's not rocket science type of thing.
Thanks.
Yeah, check if you like. Just check this with some data. You can sort of produce some data and see how that changes.